Any question about our previous session? Today we want to finish our discussion about autoregressive models. As you may remember, we start the learning procedure, and today we extend the concept to the case of conditional generation. Yes.
You don't have a class on Thursday, right? Because it's Monday is scheduled.
Oh, really? It seems like we don't have. But because the schedule for this class is almost tight. If you look at the image I uploaded in the canvas, you see that there are exactly 26 sessions. Maybe we may need to compress, for example, variational autoencoders to 3 sessions. Yeah. Okay. Any question about the previous parts? As we see, we have different type of family characterization. For example, made. This is nade still, real nade. Then we talk about made, which is an autoencoder updated such as preserve the autoregressive property. And finally, the recurrent neural network that we need to shift the input with one sample. And I have a mistake here. As you may remember, it was XL, but the true is XL minus 1 because it is contributing to generate the parameter for the last element. So XL cannot be used here. This is the contrast with common recurrent neural network. They use the XL here, but we use XL minus 1 here. Okay, and about the learning part. We see that there are different families. We characterize this subset. So now we want to characterize this path. How we can follow this path to find the best parameter in a sense. The sense comes from the distance. Okay. We have seen that KL is one of the options to calculate the distance. It is not a distance metric, but it can be approximate the distance between two distributions, and it is an expectation. It can be written as a summation or an integral based on the nature of your random variable. And we also know we know that it is 0 if the two distributions matched. So pay attention to this part. As you see here, the KL distance equal something which is just related to the data and something which is related to both data and your model. So because you want to find the best set of parameters, so you do not need this part. You can easily neglect it, but you know that when you are working with the complete term, it means that the minimum of this term is 0. But when you are working with this part alone, you cannot say anything about it unless that the maximum of this part, you see, you want to minimize the distance, KL distance, or equivalently, you want to maximize this part. And the only thing you can say about this maximum is that it is equal to this value. But we know that calculating this value exactly is a problem because you do not have access to the data distribution and you want to estimate. So if we were working with KL, we know that the minimum in this minimization, the minimum of loss function is 0. But when we are working with this alternative objective, we know that it has a maximum like this value, but we cannot calculate. Okay, so our objective is to maximize this expectation, to maximize the expectation of the logarithm of p theta of x over the data coming from the data distribution. So we can understand that a desirable situation is where that your model, this is your model, this is made, any of them you select. A suitable situation is where this model give high probability to the regions where they are probable in your data through data distribution. This objective function imposes this property. Okay, but the problem is that we do not have access to the true data distribution, but instead we have access to samples from it. And this is about the maximum we talked about. Okay, what can we do for an expectation that we do not have access to the true data distribution? We can use Monte-Carlo estimation to estimate the expectation. Okay, instead of calculating the integral, that I cannot do that because I do not have the formulation for this p of data x. Instead, I sample from it and calculate the value f here, and then average it over all data I sampled. So, using the Monte-Carlo estimation, we have this approximation, expectation of this log model likelihood. Every time I talk about likelihood, I mean the probability. Likelihood is equal to probability for us. I should assume that it is an f function. You want to calculate the expectation of this f function with respect to data coming from this distribution. So you can sample from this data, calculate the f function on those data, and average over those calculations. This is exactly a Monte-Carlo estimation, and we see that when you increase the n to infinity, it can estimate your expectation with arbitrary precision. But here we just use approximation, and n is not infinite. So I should maximize this term to learn the model. And this is easy. We talked about before. Because we know how to calculate how to density estimate for an input vector. Any problem till now? You know, the problem of learning simplified to calculating the logarithm likelihood of your model given to data samples coming from your training data. Assume that in one of the libraries, for example, PyTorch, you have implemented your distribution. For example, you have implemented nade, made, anything. Then your model is capable of calculating this probability as a function of your parameters. So you can easily call the backprop operator there, and it calculates the gradient of this with respect to your parameters. And then you can easily update the parameters until you reach a point which is our desirable point means theta star. You understand the procedure, how we train them? Is it clear?
Can you explain one more time?
Yeah. You know, previously we talked about how each of those family can calculate this value. This is the density estimation, okay? Learning is equivalent to calculating this density estimation as a parameter of your model parameters. You know, previously we talked about the case that you have access to theta, so please approximate, we can talk about theta. Please approximate this value for me, and you were able to calculate it. You give me a number, 0.00, for example, 1. Now, I said that instead of calculating the value, assume that theta is not given, but the parameters are given. Again, I want to calculate this one as a function of these parameters. For example, you told me that the result is, assume that is 0.1 times theta, the first element, plus this, for example, this is an example, it's not real. For example, the second element to the power of 2. It means that you should change this term such that the resulting value is maximized. Why? Because you are working on the data coming from true data distribution, and a good model is a model that assigns high probability to data coming from that distribution. Data is coming from the true data distribution, so your model should also give high probability to those data. So you maximize this term. Is it clear? Okay.
Just one more question.
Sure.
What does theta star stand for?
The theta star stand for the best parameter that we can find. Assume that I start to optimize this term through all the training data, and finally I reach a point, and I call that point theta star. This is the result of optimization. Yes?
Is that notation the same as writing p theta y given x, where y is the model's distribution?
To some extent, yeah. In fact, when you are working with supervised and labeled data set, you are exactly doing the same in the conditional way. And we will talk about it when we want to say the distances for conditional generation of autoregressive models. Yeah, exactly, it's the same. Any question? Okay, so let's talk about the optimization procedure, how we can find the theta star. It said that by adding a minus term here, I convert the maximization into a minimization. This is negative log likelihood, very well-known estimation in statistics. Minus log likelihood. You want to minimize the minus log likelihood, or equivalently maximize the log likelihood. So I have this minimization problem, so I can easily use any method, for example, Adam, for example, stochastic gradient descent, momentum methods, Nestrov, and any other methods you see in the PyTorch to update this, to update the parameters such that this term is minimized. And this is the learning. Until now, we always talk about a model which is given to you. Now you can train a model. We will talk about more. Okay, let's think of very, very simple examples which are not autoregressive in nature. Just talk about the likelihood and how fitting a model. I want to justify this term. Why? Maximizing this term, maximizing the expectation over data coming from the model the true data distribution of the logarithm of your model. Why this is justified as a good method to learn the model? Assume that you are all familiar with the example of tossing a coin. Assume that I am tossing a coin for 4 times, and this is the data set. You can easily extend this idea to the autoregressive model. There is no difference. We want to start with simple examples. Assume that I have a coin and toss it for 4 times. And the result of my tossing is this data set. This is exactly an unsupervised data set. There is no label for it. So I see 4 times head and 1 time tail. Now we want to optimize. We want a model, and then optimize that model. What is the best model here? What do you suggest as a model here? A model should be capable of characterizing a binary random variable because you are tossing a coin. Okay? What is a good model? Yeah, you have just one option. You have just one Bernoulli option. So assume that the data, your model distribution equals Bernoulli over random variable x, and it has just one parameter. So very easy. This is what should be here. Okay? But one important point about the Bernoulli distribution, you know that usually we talk about Bernoulli as this formulation. For example, Bernoulli of x with parameter theta mean that the probability of x equal to 1 is theta, and the probability of x equal to 0 is 1 minus theta. You can compress these two terms into this formulation. You see? How? Because when x equals to 1, it means that this parameter is active, because theta to the power of 1 is theta, and this parameter is inactive. 1 minus theta to the power of 0 equals 1. 1 times theta means theta. This term. And the other one is this term. So this is just a free formulation of the things you have seen before. So I should optimize my parameters, my theta, such that this value for this data set is maximized. Because this is the model, and this is what in reality we see from this coin. A good model should be very near to the reality. So I want to put each of these data inside this model and then maximize the theta such that the summation we see before, the negative log likelihood which is written here, is maximized. This is exactly what we do in all generative models, including this coin. Okay? What do I do here? I just put each of these training data inside the model and calculate the probability. And then the summation is 4. This is exactly this summation. Exactly this summation. Just because the logarithm, these terms are separated. Because the logarithm of this term is x log of theta plus 1 minus x log of 1 minus theta. Okay? So I should minimize this term with respect to the theta. And you can easily, because this data set is very simple, you can easily do it via gradient. You can take the gradient, put it equal to 0, and then you can find the optimum parameters. How intuitively can you say why this is the optimum parameter? Look at this data set and look at this value. Yeah, it is an empirical number because this is the probability of x equal to 1. This is the parameter. It is the probability of x equal to 1. It is exactly the empirical ratio of heads to the total of your experiments. 3 heads, 4 experiments. So it is very well justified with our intuition. Okay? Any question? Is it clear? Yes.
Wait, is this kind of like overfitting? Because if we have enough data, the number should be 1 or 2, right?
Yeah, it depends. If this data set, for example, assume that the data set is this one. This is your data set. Although the coin is not biased, unfortunately, because your number of experiments is very low, you see this data set. While the coin is unbiased, it means that the best parameter for your coin is this value. What happened? This estimation lead to the parameter theta star equal to 1. Why? Because the number of heads to the total number is 1. And this is when overfitting happens. Because your data set size is very small in comparison to the number needed, and also your data set is unfortunately to some extent biased, then you see the result is similar to it. But what is the solution in this case?
Increase the data size.
One of them is increasing the data set because you have a limited size. Another one is adding some priors over theta. It means that you have some intuition that, for example, the prior over theta is this one. You know that theta is between 0 and 1, and you add a prior, for example, this way, which promotes theta around half, 1 over 2. When you put them together, you have a new estimation called maximum a posteriori estimation, and in that estimation, you will see that it will become near to 1 over 2. This is another approach for blocking overfitting. But here also, maybe because of the size of the data set, you have overfitting here too. Yeah. Maybe the coin is unbiased, but your experiments are not large enough to handle the case. Okay. So you see here that because here the model is very simple, you can easily calculate, for example, it means again assume that we have this model p theta of x equals theta to the power of x 1 minus theta to the power of minus x. Here, assume I want to put this first element inside your model. Equals theta. So you have the distribution as a function of model parameters. This is exactly what I said in your answer. We want, now assume that you haven't made anything. You want to calculate this as a function of model parameters, but in the case of nade or made, it is not as simple as here. You have a complex relation with model parameters here, but you are not you do not want to calculate it. The framework can calculate it for you easily. Okay, so exactly the same procedure happened in your case. But here you have just one theta, but here you have a complex relation with all model parameters. Okay, so we have a generative model. You can sample from it. You can density estimate for new point, and the task we talk about in generative model. In the general case, assume that I have a data set with n samples, and h samples are head and t samples are tail. And we know that the summation is equal to n, then you can write the negative log likelihood for the data set as here. Just remember that this is the negative log likelihood for the whole data set. It means that I just do not interfere with your previous understanding of the autoregressive model. When we have a data set, we assume the data set samples are independent samples from the true data distribution, you know? So the probability of observing the complete data set is the product of each individual point because they are independent. So the probability of the whole is the product of the probability of each of them. Do not conflict it with the previous things we talked about, the chain rule in autoregressive models. So this is exactly the likelihood for the complete data set. And if you calculate it, you see that the term we were looking for is equal to this one, and the result is nh over n. You see that the result of the maximum likelihood is always an empirical value. Empirical value means something coming from your experiment. It is an empirical value. It is just the ratio of number of heads over the total number of samples, which is intuitively a good option because in your data set you have seen NH heads between N experiments. And this is the probability of H. Any question? And this is your model. So these two were very simple examples of learning a model based on maximum likelihood estimation. Now, if you want to learn a nade, made, pixel RNN, or etc., what can we do? Assume that I have access to this data set, which is, for example, these are the samples of MNIST, and I want to train a made over the MNIST data set, for example. So first, I select a mini batch B of samples with size n prime. Then I compute the loss function in a parametric form. This is not done by you. The framework can easily calculate this loss. You see that this is the negative log likelihood for the data coming from your batch. And this is divided to the batch size. So you have a parametric form of your loss function with respect to the model parameters. So I should update the parameters such that this loss is minimized. And this can be done using any of the methods, for example, stochastic gradient descent, any of them in PyTorch or TensorFlow. So you will get a gradient with respect to the parameters and then update the parameters using any of the gradient-based optimization methods. And repeat this procedure until we reach a convergence point. So can you imagine now how you can train an autoregressive model easily? For example, assume that you want to, a best practice is to write, for example, a nade model, a fully visible sigmoid belief network by yourself without any of the libraries, and then try to optimize the parameters for that model. You can then easily understand what's happening there. Assume that in any of the framework I have my model. What do I do? I have the samples from MNIST data set. I call it D. I take a bunch of samples from here and then give it to my model and calculate this L of theta as a function of model parameters. This is a functional form. In this functional form, I can calculate the gradient with respect to the model parameters. And if I have this value, I can update the parameters such that this is the learning rate, for example. If I update it here as this relation, then hopefully I have a model. Assume that this is theta 1, this is theta 2. Hopefully I have a new model with these parameters, and this theta 2, assume again this is the best, this is your P data. This was your initial point theta 1. By this update rule, hopefully I am going toward a better point nearer to the true data distribution. Okay? And by repeating this procedure, I hopefully reach this point, which is in the nearest distance to my true data distribution. And the final value of theta is your final model. And that model can be used for generation, for density estimation, for any task we talked about before. Okay, everything is clear? Yes?
The reason that you are using gradient descent is because finding optimal theta is costly or not possible?
The
exact theta
Yeah, so
sum.
in the previous example, you just calculate the
yeah. That was because the model was very simple. When the model is complex, the resulting loss function is highly non-convex. Highly, not non-convex. It's highly non-convex. It has lots of maximum, minimum. Yeah, it has several problems. Yeah, and you cannot find easily in a closed form solution. Yeah. You have a question, IP?
Yeah, so the theta star there is like a global minimizer, right?
No.
It is not global.
It is a minimizer, local minimizer, yeah. Because they could not because the loss function is very non-convex. It is not easy to optimize. You know, the function here, this function is not a very easy function. It is lots of nonlinearities, lots of several things. Assume that, for example, the maid have several nonlinearities inside. Each node, each neuron have its own element-wise nonlinearity. They are all here. So it is very complex. It is exactly the same as training it, for example, a deep learning model. Can you find the global optimum for the deep learning model? No. You just find the approximation, a local minimum. Yes. Any question? Yeah, this form is very complex. Do not assume it as a neat function. It is a very complex function. You cannot you cannot even talk about the global optimizer of this value. Okay. So now we can train a model, we can generate, and also density estimate for new values. The most important point, how is overfitting handled here? As you talk about, the overfitting problem is always in our models. So, when you have, assume you have lots of parameters, one approach to decrease the probability of overfitting is to limit your family. Make your family smaller so that you have a smaller number of parameters, and then you have the ratio between your number of parameters and your dataset size will be, the dataset size over the parameters will be increased, and consequently the result, the chance of overfitting will be decreased. Assume that instead of, for example, xi can be related to all previous ones, but in my case, I assume that it is just a function of the two previous ones. This may be logical, for example, in text modeling. For example, you assume that the probability of this word is just dependent in two previous ones, maybe, because totally the text is also dependent on even on the future. Consider a total sentence. Some words, the meaning of some words may be dependent on the future, but assume that for our case of controlling the chance of overfitting, we assume that each word is a function, the probability over each word is a function of just the two previous ones. So the size of the model will decrease, and as a result, the ratio, because one important point is the number of your training data over the number of parameters, model parameters. If this ratio is increased, generally the chance of overfitting will be decreased. It is in your supervised model, you also see that. This is one way to decrease the number of parameters, just dependent on two previous ones. One of the most important approaches is weight sharing that you see in NAID and RNN. RNN was the best example for weight sharing. You see that independent of the length of the input, the RNN parameters, number of parameters is fixed. This is a very great property for the RNNs.
Are there like theoretical guarantees for that ratio? So that
no, it's just a rule of thumb. There is no guarantee. Just a rule of thumb. If you increase the number of training data over the parameters, it means that the chance of overfitting to some extent decreases here. So weight sharing is also another great opportunity to control overfitting. The other one is weight decay, that we generally know as it is equivalent to putting some priors over the parameters. As we talk about in the case of the coin, I said that, for example, you see all head data set. Also, the coin is unbiased. Then you infer. Then your estimation is that the parameter is equal to 1. Equivalently, you can put some priors for this theta, such as the prior I've talked about. For example, this prior 0, 1, which promotes the value of 1 over 2. So this is a prior. Again, for the deep model, for DeepL models like MADE or other types of model, you can put some priors like weight decay. Weight decay, assume that I put the prior of weight decay for this parameter. It means that I assume that it has a Gaussian distribution, normal distribution with mean 0 and sigma 2 variance. When you add weight decay, it means that you are in the back of your action, you are assuming that that parameter has a Gaussian distribution with this mean and this covariance, and you generally add the weight decay with a lambda, which is the hyperparameter. This hyperparameter is directly related to this sigma value you assume for your prior. But we do not want to talk about this part of the weight decay. Just add this term to your loss function. It can control the model. Let's say justify it based on our approach of characterizing a family? Assume that this is the family of MADE. When I add this term to your loss, our loss we know that is negative, a summation, a log, a likelihood. This is our loss. This is our loss, and I add this term to our loss. How can it affect this set? Just intuitively, not in a theoretical or provable way. But how? These are the parameters. I add the weight decay for all parameters of my model, irrespective of their role. For example, some of them are biased, some of the matrices. No, I do not want to pay attention to their role. Just add this value here. What happened to the family? Yes?
I think the constraints, like if the higher lambda is, the lesser the data is going to affect.
Yeah, the higher the lambda is, the parameters cannot be flexibly changed because they are constrained to be near 0. It is okay? It is understandable? Because when you increase the lambda, irrespective of your data, you want a model where its parameters are all concentrated around 0 because they minimize this term. Because the lambda is a large number, so this term is much more important than this term. Consequently, all the theta is contracted around 0. It means that this family is not flexible enough. You have a very smaller family. The parameters cannot be expanded arbitrarily based on the data. They are also constrained to be around 0, which is irrespective of data. This term does not depend on your data set. Data set does not affect this part. It says that just theta should be 0, near 0. The parameter of your model should be near 0, irrespective of your data. It means that the family is contracted. It is just intuitive, not a very provable approach. But again, I mean that using this term, it means that you are minimizing your family. Okay, if we want, we can talk about this topic after the class. Especially in the case of the coin, you can easily understand why this approach, in the case of the coin, in the general sense, your theta parameters can be effectively between 0 and 1, and dependent on your data set, you have selected 1. But this prior, which is to some extent equivalent to weight decay, imposes that theta to be around 1/2. It means that it cannot be far from 1/2 because this is the highest probable value of theta. And in this way, you are contracting the family. Although in the general case, the family is the theta can be between 0 and 1, and data characterize it. Here, the data does not have the complete control. This prior term also imposes that the theta around 1/2 is a probable case. Okay? We can talk about it further after the class. Let's continue our discussion. And one important point about autoregressive models is that you can also assume that I have a data set, I have a validation data set. How can I use the validation data set to control overfitting? Exactly similar to the supervised case. You can, when you are updating your model, you can calculate the negative log likelihood over the data coming from the validation set. Okay? These are the data coming from validations. They are not the training set. You can easily calculate the probability for data I give you, okay? So you can easily calculate this value and then plot it here as a function of epoch. In some cases, you see that you are minimizing this term, and suddenly it's start increasing. So you can stop your process here. And this is the best model. This axis is not the theta axis. It's the epoch. I mean that in this point you have your best model because it is best generalizable to data coming from your validation set. This is another approach to control overfitting in generative model. We generally do not have access to this approach. You will see that, for example, in some cases, you do not even have the likelihood. You cannot calculate the likelihood. So these are the methods you can avoid overfitting. So let's talk about conditional generation. Conditional generation is simple because it is a repetition of what you have previously seen for supervised learning. Any question about the previous part, about the what was that part, about the overfitting? Okay. Assume that I have some extent a conditional generative model where you have x and y. So y is, for example, the text, x is the corresponding speech. For this problem, similar to supervised learning, we are interested in modeling p of x given y. The justification for changing the rule of x and y is here. As you see, till now we talk about this random variable and the distribution over this random variable, for example, the model distribution. Now we just want to talk about the distribution over again x, but some information, which is this is a vector given to you. This is not a random variable now anymore. Very simply, it can be extended. You know how? For let me talk. Oh, we do not have. Oh yeah, we have something here. Let's talk about. So similar to supervised learning, we are interested in modeling p of x given y. You see here that I write y, it is not a random variable, it is just a vector. This is a given vector because it is on the condition. Thus, on the conditional distribution P of y is not modeled. It means that we do not see y as a random variable. We just see that as a vector, input vector, like supervised learning. Just the name is changed, nothing more. So, but in contrast to supervised learning, in supervised learning, you want this x in your mind, you assume y, because we changed the notation. This x was a label. It was between 1, 2 till C. Assume you have C classes. But now you are working on the case where this x, for example, is the speech corresponding to this text. This text is, I am going home, for example, going home. This is your text, and the x you want to generate, for example, is a one-dimensional speech. If you play it, you're using your player, someone is saying, I'm going home. So it is a very high dimensional random vector, in contrast to your previous case. Okay. Modeling. Here, keep in mind that y is in Rg is a vector, and we want to model p theta of x given y. So just to see how our autoregressive model changes when we have a condition. Previously, when modeling p of x, we said that the chain rule says that, let's talk about the random variable. Chain rule says that the first variable is independent of anything. It is an unconditional distribution. The second one is conditional over the previous one. This is a vector till the end. Let me write the end one. Oh, less than. This is the chain rule. Okay? What happened here? Just a very simple input is added to all of these terms, and that simple input is y. This is not a random variable, it's just a given vector to you. It means that, let me fill it. Previously, to design the distribution over x1, we have this term, as you remember. We have a bias term, it was input into a summation, but because we have no condition other than, no condition for the random variable over the first element, we have nothing here, and then we go through a sigmoid, and then the lambda 1 is generated, and then we assume that x1 is distributed as, assume it is Bernoulli of x1 with parameter lambda 1. This was our previous work. Now what happened, instead of just having a bias term, y can also be input to all of those calculations. It is given to you. It is in the data set. For example, in the supervised learning, you have access to your image and you want to have something to say something about the probability of each label over that x. The label 1, 2, 3. Here is exactly similar. This x is converted to y, a vector, so I can add it to the bias term. If this is a scalar, it can be easily added. If it is not a scalar, it should be multiplied by a vector to be a scalar, then, for example, then be added to your bias term. So there is nothing more about conditional generation. Just one vector which can be added to all conditional you are calculating. Is it clear? We will talk about it further, and especially maybe in your homework, if you have generative autoregressive model, you can think of it. But if you have any question, we can talk after the class and also in the office hours tomorrow. So just one term, one input is given to you, which can be used in all of your factors. You see here, the first factor, second, third, all of them can be used. This is the information provided for you. Assume that, for example, in a model like ChatGPT is in the nature is based on autoregressive modeling. You will see that when you input a prompt into ChatGPT, it starts generating the data. It does not totally show you the result. It starts generating data, and because it is an autoregressive model, it cannot infer the total text in your reply in one step. It starts generating the first element, the first word in your response, the second, the third, until the last. And it is conditional generative. Why? What is y? What is this random variable y when you are using ChatGPT? Exactly, your prompt. Your prompt is this y. You are given this y. So ChatGPT can use your y to know what is the first word in your response. Because before starting the generation, you give it the y. Okay? This y can be used to infer the word in any place of your response, as you see here. This is the first word in your response, the second word, the 10th word, and the last word. And in all of them, the model can use your prompt as your input. And also the ChatGPT uses his own response, previous words. In the future, it means that, assume you ask ChatGPT, for example, what's the time? In the first step, ChatGPT converts this prompt into some vectors. The way it splits this sentence into parts is not based on word, is not based on characters, is something in between. Sometimes it uses words, sometimes it uses subwords. It is different, okay? Based on my intuition and my search over the ChatGPT. Okay, so all of the input data is converted into several vectors. These vectors can be considered as the y. What happened next? ChatGPT wants to start a response to your question. So it should fit based on, assume that it has a model. It has a trained model. Okay, it should model this distribution. So it inputs the y into his model, and then generate a distribution over all possible tokens. There are lots of tokens. So one of those tokens has a higher probability. They have different probabilities. Then what happened? ChatGPT sampled from this distribution. Sample, it means that one of those words with highest probability will be shown to you in the screen. So, for example, it shows you it. What happened in the next step? ChatGPT modeled this distribution, P of x2 given y and x1. x1 is this one. Because x1 is generated, so it is a vector. It is given to you. And ChatGPT, in its nature, can model it. For example, it has the RNN. RNN is irrespective of the input length. It can do anything. But in the nature, it is a decoder of a transform. Oh, okay, you have a new distribution over the second token. The second token know if the first token, and also know what is your prompt. So based on both information, it gives probability to all tokens, okay? And consequently, you again sample from it. For example, the second token, then the result of sampling is. This is your second, x2. Again, ChatGPT continue this procedure, but in the next time, it uses this distribution. The probability over the second token given the previous ones, which we show by what? Less than 3. These are exactly our notation. Less than 3 and the prompt. It means that it knows what it previously answers you and what you input to the model, and then fit a new distribution for the third token. And again, sample from it, continue this procedure until this sampling from this distribution show as token which is end of sentence. This is also a token. End of sentence means everything is finished and you can show the user the result. It starts, for example, what is the time? We say it is, for example, 12 o'clock. And then after o'clock, the ChatGPT outputs EOS. It means that the response is finished. So this is the EOS. Okay? But one important point, you previously see this metric because you have worked with supervised learning. In supervised learning, you use the same idea. We want to talk about how we can, what is the distance for generative conditional generation in autoregressive models. Okay, previously we see that the distance was the KL between the true data distribution and your model distribution. This was the distance metric previously. We taught these random variables. Here, inside this part, you have seen the distance for one, for example, for one prompt, for one input. But it is not suitable that for one prompt your distribution and data and model distribution match each other. What happened? We add an expectation over the data coming from the true prompt distribution. But we know that we do not model this one. You can see that this formulation is transformed into very simple form. But in nature, we are working with exactly this loss function. It means that for one prompt, we are minimizing the distance between the data distribution and model distribution, and then take the expectation of this KL loss over all possible prompts. This is a very general distance metric. It means that both of these x and y are assumed to be random vectors, and we are working with different prompts or different conditions or different y's. So what happened? We know that the expectation with respect to a distribution means that you should multiply this function using this distribution here and then average it over all possible y. We know that we do not have access to this part. So if we transfer the logarithm of the ratio into the logarithm of the numerator minus the logarithm of the denominator, we have these two terms. What happens here? Exactly similar to the previous for unconditional modeling, the first term is independent of your model. You see, this is the expectation of the conditional distribution over the joint distribution, over the data coming from the joint distribution. So this is a term irrelevant of your model parameters, so you can easily omit it. But this term is dependent on your model parameters. And it is very intuitive term. Here I write that the first term is irrespective of theta, so it can be omitted from the objective function, and you can save the second term. So instead of minimizing this distance metric, we can minimize the expectation of, I omit the negative sign here. We can minimize this, we can minimize this function, maximize this function. We omit this negative sign here. So something happened. You should have data coming, if we want to approximate the term using Monte-Carlo estimation, we should have samples coming from the joint distribution. Do we have access to this joint distribution sample? What is the training data, for example, in the simplest case? What is the training data for ChatGPT? The training data, for example, in the conditional sense, are X and Y pairs n X and Y pairs. Because here we have conditional generation. It means that you must have an input for each of the cases. For example, if it is MNIST, you should have, for example, the label in the conditional generation. For example, if you have a grayscale image, you must have the color image in the training data. If you assume that you want to train a model that transfers a grayscale image into a color image. This color image is random variable X. This grayscale image is input Y. So you have several of data samples. This is the color one. This is the grayscale one, and you can easily generate it as we talked about before. That you can take the X and then transform it into grayscale using PyTorch, for example, or Python, and then you form your data set. So, what is the data coming from the joint distribution of true data distribution? These samples are samples coming from the joint distribution. You know? Why? Because they are samples where the probability of the joint model is maximized. Why? Because they are generated, they have been seen. They are corresponding grayscale and color images. You know, in the true data distribution, the optimum, for example, this is a color image of a scene. Then using, for example, Python and a library inside the Python, I change it into a grayscale image. In the true data distribution sense, a true data distribution, if you input these two images into your model, what do you expect? Do you expect it give a high probability or low probability? High probability, because they are really corresponding to each other. The best case, because you yourself transfer the color image into a grayscale image, they are completely corresponding to each other. And and in the true data distribution sense, they must have a high probability because they are really coming from the space you are modeling. Okay, so these samples are easily samples of your training data set. And if you want to calculate an expectation over this distribution of this function, you can easily, this is just talk about the things we talk about here. You can easily sample from this distribution, means select some of the training data and then calculate the F function and then average it. This is what you previously done in supervised learning. In supervised learning, you are exactly doing the same. It means that you are in supervised learning, we are minimizing this loss. The expected loss, just the notation X and Y is changed, nothing is changed. You are minimizing this loss. Here also we use the same and see that the result is to maximize the logarithm of the likelihood of the conditional instead of the unconditional here. So nothing changed, just the condition is added to your model and it can be used for any of the terms you use. This is the most important point about the conditional generation is this term. Your vector, your prompt in ChatGPT can be used to generate each of the word the model is generating for you, and also the model also access to the previous word generated because it's an autoregressive model. Then it is the autoregressive condition. Okay, we can talk about it further if you have any question. Any question about the conditional generation?
Just one.
Yes.
Why did you change the notation?
Yeah, the change of notation is for this. I assume that during the conditional case, on the conditional case, I talk about these factors. Okay? Here, I can easily talk about, again, the random vector is not changed. This is small x, lowercase x. Just to save the random vector, the notation for the random vectors I am modeling, nothing more. You can easily change if you are comfortable with the previous notation of your supervised learning. Any question? Okay. We have just 2 slides. There are some applications for generative modeling that some of them are in your homework too. I think you will see the anomaly detection in your homework. But there are some also more severe cases like adversarial samples for deep learning models. As some of you may be familiar with adversarial sample or adversarial robustness. Assume that this is a legitimate sample of your model. The model is, for example, a model used in an autonomous car that can detect the type of the sign its inputs. This is input to your model, but if I add this perturbation to your input, you have the same image. They are exactly the same, but this perturbation is inside this image. And if you input your model, the clean image, it outputs a stop sign. But unfortunately, after adding this imperceptible perturbation to your image, the model output yield sign, and it is very dangerous for an autonomous car. This is the problem with deep learning models, that they are not as robust as human, because the human do not change its inference for these 2 images, and even much more noisier versions. This is a very simple task for human. It is a trivial task to some extent. Okay, but how can generative modeling help us with this scenario? Look at these images. This is a clean image, which is a frog. This is again that image, but a random noise is added to your frog. You see that you do not have any changes here, and you again still infer that this is a frog, but a model output bird. And these are the methods designed to design these are the models that design the perturbation intelligently, more intelligently than random. For example, this is a FGSM method. It output cat. This is BIM, another method. It output bird. You can see that it just adds some perturbation here, and also some of them inside the image. And this is DeepFool, which outputs airplane. This is CW attack Carnegie Wagner, which outputs birds. Although all of them are frog for human. Okay, what happened here and how we can use generative modeling here? Maybe we do not have time. This needs more time to be explained. We will talk about just this last presentation, last slide, and then we go to the variational autoencoder. Variational autoencoder is much more, let's say, theoretical background, theoretically justified model, and you will see that we will reach the latent variable representation, which was one of our tasks in generative modeling. If you have any question, you can talk. If you have not any question, thank you for coming to class.